Hey everyone, welcome to Dave's Hack Shack. Today we're going to discuss tutorial number 1, the power supply and voltage monitor for my 5.5 watt laser tank. The laser tank is powered by a LiPo battery rated at 2200 milliamps with a voltage of 11.1 volts. Our LiPo battery is labeled as an 11.1 volt battery. However, once it is fully charged, the voltage can be a little bit above 11.1 volts. In our particular case, it's 12.6 volts. That's nothing to be concerned about. However, it is significant to know because we're going to use that information to properly align our voltage monitor circuit. I implemented the voltage monitor circuit to keep the battery healthy. Now, normal use of the battery causes it to degrade over time. And to prevent further degradation, you don't want the battery to discharge too low. So inside the voltage monitor circuit, I implemented a low voltage cutoff or LVC of 10.5 volts. Now I'm not going to get into the details of LiPo batteries and why you need such a thing. However, I did provide a good link to a guide for one. The tutorial shows code using a software interrupt with an interrupt service routine, some background processing, and the battery monitoring code. At this time, we're only going to focus on the battery monitoring code. I'll discuss those other functions in future tutorials. So with that being said, I will be adding multiple sensors and devices to the laser tank. So I wanted to ensure that only certain processes take up CPU time, including the battery monitoring. Our power supply requirements include 10 to 12 volts for our 5.5 watt laser, 9 volts for the left and right drive motors, 5 volts for the Arduino and some other control logic, and a 0 to 3.3 volts DC value that's directly related to the 12 volt battery's health, i.e. 3.3 volts is equal to 12.6 volts on the battery. We use this to calculate the current and average battery voltage. Here's a picture of the laser tank I currently have under construction. As you can see in the picture, I have the power supply and LiPo battery installed. I've also included the full electrical schematic. It includes the 5 volt supply, the 9 volt supply, the 12 volt supply, and the battery/voltage monitor section. Now the voltage monitor section is comprised of two pieces, a hardware piece and a software piece. The hardware piece is a simple voltage divider circuit, where by adjusting R2, I get a voltage of 3.3 volts when the power supply voltage is 12.6 volts. The 3.3 volts is fed directly into our Arduino on pin A6. A6 is configured as an analog input, and that analog input is fed directly into our analog to digital converter. At that point in time, the software takes over. The voltage monitor software is driven by an interrupt service routine, which is then processed in the background. The software is designed to take a sample every 3 seconds and then take the last 10 samples and create an average. That average is the basis for the LVC decision, or the low voltage cutoff. That's what we use to tell the user it's time to shut down the tank. The voltage monitor software is broken down into several unique areas. However, when we combine those areas, we get a complete solution. The first area we're going to discuss is the define/system variables. Here's where we define our input voltage, our low voltage LED, our actual voltage cutoff value, and a few system variables that were used for reading, averaging, and control. The send battery status is the heart of our voltage monitor program. So let's walk through that one line at a time. As you can see here, the first line is where we actually read the input voltage on pin A6 using our analog to digital converter. That gives us a raw read value equal to the resolution of the analog to digital converter, which we have configured as 12 bits. That will give us a value from anywhere from 0 to 4095. So we take that raw read value, times it by 12.6, and divide it by 4095. That gives us our actual floating point battery voltage, or the current voltage that we're reading at that time. We then take that battery voltage and we start to build our average. Now remember, we said we take 10 samples to get the actual average. So here in this section, we're actually taking those 10 samples, we divide it by 10, and we get our final average voltage. That final average voltage is the one we use to compare to our low voltage cutoff value. If it's at or below the low voltage cutoff value, we'll send a message to the user letting them know that, hey, we're below below the average value, light the low voltage LED. If not, we'll make sure the low voltage LED is on and continue on. Everything's okay. As I had mentioned earlier, we check our battery status every 3 seconds. And we're able to do that because we configured a software clock that generates a 10 microsecond interrupt. And every time we get that interrupt, we call our interrupt service routine. And within that service routine, you can see here, is where we actually count those 10 microsecond interrupts until we get to 3 seconds. We then stop counting, which then tells the background to check the status. And once it's done, it resets the clock and the process starts all over again. Now you're saying to yourself, why 10 microseconds? That's pretty fast. Well, we need that value for our 5.5 watt laser, and I'll explain that in a future tutorial. Every Arduino program has a couple of required code blocks. One of them is setup, and the other is loop. And the setup function is typically where you initialize your variables, set up your hardware, or run any required functions you need to make sure your system is running correctly. In our setup, you can see here we initialize our input-output pins, we set up our analog to digital resolution, and we run our first battery check. And the reason we do this is we make sure that the battery is a sufficient voltage at startup. Otherwise, we give the user a warning and set the low voltage warning light and don't really proceed any further. This way we're not running the system, or we don't allow the user to run the system when we have a low battery. The last section of our voltage monitoring software resides in the loop function. Now the loop function is a required Arduino code block. Typically in the loop is your main program and its processes, and as the name implies, continually loops back and forth. In our loop function, we've added one process called background process number 1. Its function is to sit there and wait till the interrupt service routine reaches 3 seconds. When it does, we reset the counter to tell the interrupt service routine to start again and check the battery status. And then the whole process starts all over again. Well, that's the end of this tutorial regarding the voltage monitor software on my laser tank. Now keep tuned for future tutorials as we continue to develop the laser tank. All the information is available on GitHub. And thanks for hanging out at the shack.